So in this lesson, we're going to introduce forces that dissipate and thermal energy. Up to this point, we've been thinking about objects, and we can do work on them. So we apply a force over some distance, and we do work, and that work changes the kinetic energy, or can change the kinetic energy. Okay, but what happens when we have things like friction involved? So to start thinking about that, we got to expand our view of energy in the system, and we need to zoom in on the microscopic level. So this is just some system. And so within the system, we would have these particles. And each of these particles, they're moving around inside of the substance. And they could be moving at any direction with certain velocities. I drew these all, they look the same, but they're not. So, you could have little ones and big ones. And so these things, they have kinetic energy. So they have of particles, we'll say. But they're also bound together with chemical bonds. And so these chemical bonds are similar to springs. And so these things store up potential energy. So when we're looking inside of the material, we have both kinetic and potential energy. And so we can define thermal energy to be that quantity of both of those put together. So the thermal energy would be the kinetic energy of the particles, or we could say the microscopic, plus the potential energy of the microscopic. And that's what we're going to refer to as thermal energy. The reason that we call it thermal is because we can actually get a measure of it using a thermometer, and that's what we refer to as temperature, is the amount of energy stored within a substance. So the faster it moves, the hotter it is. And so now when we're looking at a system, we need to consider both the macro and the microscopic energies. So our kinetic energy and our thermal energy. So we can expand our work energy theorem now, that the change in energy of a system would be the work done by an external force, which would result in a change in kinetic energy and a change in thermal energy. And then we can work with this the same that we did before. So all we're doing is we're tacking on this piece. So dissipative forces that dissipate energy. So we got to think again what happens as an object, say object A up here, is sliding across object B, and we have friction. So as it's moving, basically what you have is these particles interacting, these particles at the surface. And so they'll be attracted to each other, and so they'll form these bonds, store up energy, and then it gets released once they break that bond, and then you'll have a change in kinetic energy. So in this case, we have both a change in potential and a change in kinetic. And again, I'm talking at the microscopic. Now, the thing is over here, you're going to have the same thing. You're going to have a change in potential and a change in kinetic energy on both surfaces. And it's for this reason that when we have friction, both objects have an increase in their thermal energy. And so we'll use this when we talk about work. And really when we get to conservative versus non-conservative forces. But anyway, I don't want to get into that. Okay, so let's think about a box. So we're pulling a box with some tension across a rough surface, no acceleration, so we have constant velocity. So since we have no acceleration, we know the net force is going to be zero, which means that the tension minus the friction, the kinetic friction on the other side, is equal to zero. And solving for that, we can see that the tension is equal to the kinetic friction force. So now we can use the work energy principle. So the change in energy would be the work done by tension, which would be tension times the change in position, the displacement. And so notice on this next one, I write the change in energy is going to be, I can substitute. I said that these are equal, so now I get the kinetic friction times the distance. But this is not work. So these are not the same. This is not work. It's just a change in energy. All right. So now a change in energy would be a change in kinetic plus a change in thermal. And since it's moving at constant velocity, there's no change in the kinetic energy, leaving the change in thermal energy. So the change in thermal energy will be defined as the kinetic friction force times the displacement. So it's similar to work, but not work. Okay. The reason for that is because the energy goes into both objects. So we're not putting energy into one, if that makes sense. It'll make more sense once we get into conservative versus non-conservative. We're pulling a 10 kilogram object across a horizontal floor with a tension of 30 newtons. It starts from rest. The velocity is 0 to begin with. It's not written up here, and then we have this frictional force, and we're going to pull it across 3 meters. So we want to know the change in thermal energy and the final speed. The change in thermal energy we can do as a little side. So the change in thermal energy, I go back and forth between U and E. Don't get caught up. That would just be the kinetic friction force times the displacement. And then the friction force is going to be the coefficient of kinetic times the normal. And the normal in this case is, you can see Fg is straight down and the normal is straight up. So it's equivalent to mg. So we get the coefficient of kinetic times mg times delta x. If you plug in your numbers, 0.2 times the mass, which is 10, times g, which is 9.8, times delta x, which is 3. You run that calculation, you get 59 joules. So we have 59 joules. The thermal energy is spread between the box and the floor. Okay, but really what we want to do is set up the entire principle. So the change in energy of the entire system would be the work done by the system, which is now our change in kinetic energy plus our change in thermal energy. Okay, so we're going to work with this equation here. So the work done is going to be my tension times the displacement. And then my change in kinetic energy would be kinetic energy final minus initial. And then that would be plus the change in thermal energy. And then I can move this over to the other side. So we get the tension times delta x minus the change in thermal energy is equal to the change in kinetic energy. All right, let's see what this, let's make sense of this. So let me change colors. So what we're looking at is the tension's doing work on the object, but some of that work that it's doing is being lost. We're subtracting some of it away that's going into thermal energy. So the resulting change in kinetic energy is going to be less than what it would have been. All right, to finish out this problem, the initial kinetic energy is 0. So we get tension times the change in position minus the change in thermal energy. It's going to be 1/2 mvf squared. The 59 joules would go right in here. I'm not going to do that though. So multiply by 2 and divide by m. Just make sure when you multiply, you do the whole thing. So it's T delta x minus change in thermal energy divided by the mass, and then take the square root. So just a little bit of algebra. That would give you the velocity. All right. So whenever you're working with this, stop. When you get to equations, make sure that they're making sense. And again, so the work minus the change in thermal energy gives me my resultant change in kinetic energy.